Hi, my name is Hannah Brooks, and I'm currently a PhD candidate at the University of Maine, working with Carl Kreutz on ice cores from Biguya in Alaska. And today I'm excited to present some new data showing the fluctuations in the lead concentration and the lead isotope ratios at this ice core location. Before we get started, I just want to take a moment to acknowledge that the Denali ice cores were recovered near the summit of Biguya, which lies within the traditional homelands of 6 sovereign nations who have occupied the region for thousands of years before our study. Additionally, any research conducted at the University of Maine occurs in the homeland of the Penobscot Nation, a member of the Wabanaki tribal nations. So just to set the stage, the idea of measuring cryosphere, snow, and ice records to examine changes in lead is not new. In this map, what we see, each dot or line represents a sampling site where someone has run around the globe and collected snow and ice to measure its lead concentration and isotope ratios. So we can see that there's a pretty good distribution of these records around the globe. Of course, it is centered around the cold places with glacial activity or heavy snowfall. So we see a lot more records in the North and South Pole than we do in South America. The other thing to note is each of these records has been color-coded based on its temporal length. So there's a lot of records in Eastern North America. However, they all happen to be 1 to 2 years old. Whereas when we get to mountain glaciers and to the ice shelves and caps, we can see that these records can be much, much longer in length. So what we know from all of these sites that we've previously looked at and those published records is that we can see that there's been a distinct change in the amount of lead as well as the lead isotope ratios recorded at these locations on the globe through time. So this plot, we have the ratio of lead 206 to 207 on the y-axis, and we have 208 to 207 on the x. All the data is color-coded based on the region of the world that it came from, and you can see that while most of the regions cluster really tightly in the pre-industrial time frame, so before 1770. By the time we get to the modern age, we can see distinct lead isotope signatures for each of these regions globally. Importantly, not all of the records have really long time spans to them. So, for instance, we don't have any North Pacific records from the pre-industrial at present that show us lead isotope ratios. So another consideration that we have to think about when we decide where we want to go and gather these cryosphere records is that we want to make sure that we understand what signals we're actually getting deposited at our ice core site. So because of the global transportation of dust and aerosols around the planet in belts of wind, we can actually back calculate where this wind was most likely to come from. So lead hangs out in the atmosphere for about 5 to 10 days once it's emitted from a source. And what we're showing here are calculated back trajectories where the yellow is the least likely places that these signals are coming from, and as we go from green to blue, the blue is the most likely, the highest confidence that we're sampling wind from that location. So we can see that if we are interested to understand what's happening in, say, Eastern Europe, then a site such as Everest could be a really excellent fit. So today we're looking at a record sampled from Alaska, and if you look at panel A, you can see that this means that we're sampling wind that has transported from East Asia across the North Pacific Ocean and been deposited in Alaska. So that's the source that we're expecting for our lead pollution. So here is the long-awaited Biguya ice core lead record. It's a very high resolution record with one sample every 20 centimeters, and it spans from 340 to 2022. And what we can see, as we would expect, as time increases on the x-axis, the amount of lead concentration that's being deposited at this site increases from, almost negligible or 0 parts per trillion around 900 CE to, by the time we're in the 2020s, we can regularly expect that signal is above 50 parts per trillion. We can also see wiggles in the lead isotope ratio signatures, which is expressing changes in the lead sources that are being deposited. So the biggest question that we are asking ourselves right now is, what changes are we actually recording over this time? So this is a zoom in of the ice core record from 1950 to the present, really zooming in on some of those smaller scale variations that have been affecting lead in the modern times. And when we compare that to estimated and known emissions from countries such as China, we can see that some of these variations that we're seeing in our ice core record can potentially be contributed to changes in non-ferrous metal production, in coal consumption, in liquid fuel consumption, as well as lots of other sources. When we compare the Biguya lead record to other published records, what we can see is the similarity in the lead concentrations in Biguya, which is in Alaska, as well as Mount Logan PR coal record from the Yukon. Whereas there's a deviation when you compare the Biguya record with the Greenland record. In Greenland, we very clearly see the onset of the American and European Industrial Revolution, which is absent in the Biguya or Mount Logan records. We can also use these records to show exactly how powerful the Biguya ice core record is with its high resolution sampling, whereas most long records only have a few samples discretely through the record or have a high resolution but very short temporal length. The Biguya record spans a lot of the changes that have happened in lead emissions due to human-caused pollution. Currently, we're working to see if we can actually pin those individual lead emission sources that are impacting the Biguya record to known sources. So here we have plotted lead data from 340 to 1000 CE. Those are the gray to black colored dots. And we're plotting them alongside known emission sources that have published lead isotope ratios. And we're examining to see where the overlaps might be, what might be contributing to the shift to higher lead 208, 207 ratios that we see in our record as we move through this time span. As you can see, there's pretty poor correlation with things such as dust, but that ore mining actually has a really good correlation with our data set. And perhaps we can fully explain the changes we see in the record looking at the co-varied sources of ore mining, dust, volcanics, and copper. So just to recap, the Biguya lead concentration and isotope ratio record is unparalleled when you consider its resolution and length and compare it to other global records that exist. Early analysis indicates that the Biguya record shows that the majority of the recorded lead emissions are from East Asian countries, including China and Japan. Over the length of the record, there have been significant changes in the amount of lead that is being deposited, and we can also see clear changes in the sources of these lead emissions. We are continuing to work to understand exactly what changes have been recorded.